Determining our total pressure ratio will give us will take a little more work. We know that our total pressure outlet, PT2, over total pressure in, PT1, is going to be equal to our stage efficiency, eta 1, 2, again, times this change in our rotor speed times the change in absolute tangential velocity, cu2 minus cu1. We've kind of made the assumption we're at a constant radius there. But we also have to divide by the specific heat times our total temperature. Then we have that plus 1, everything raised to the gamma over gamma minus 1. So we were given a static temperature. We need a total temperature here. So that means we're actually going to have to go back and to look at our speed of sound and determine our Mach number at the inlet to the stage, and then determine the appropriate total temperature. So we need to know basically at the inlet to the rotor what is A1, which we can calculate as the square root of gamma times our given static temperature T1, and from that we can calculate the absolute Mach number at 1, just based, of course, on the velocity of our inlet flow divided by A1. We can calculate the speed of sound just based on our gamma value of 1.381 times the value of the gas constant, 53.35, and the units there are foot, pounds force per pound mass, degree Rankine, times our static temperature, which was given as 900 degrees Rankine. Then to get our units straight, we need to convert our pounds force over there. We're going to just multiply by 32.17 pounds mass feet per second squared per 1 pound force. So that'll leave us with units of feet squared per second squared inside our radical, and we can get that our speed of sound is 1,461 feet per second. So our Mach number, therefore, if we pull down the magnitude of our absolute flow velocity, it was 749 feet per second from what we calculated earlier, dividing by our speed of sound, 1,461 feet per second. We're going to get a Mach number, absolute Mach number of 0.513. We can then use that together with our isentropic flow relationships and the given inlet properties to get an inlet total temperature of 945 degree Rankine and an inlet total pressure of 167.1 psia. So now we're able to actually evaluate our total pressure ratio, PT2 over PT1, which is going to be equal to 0.88, our stage efficiency, times U, which was 866 feet per second, times our change in absolute tangential velocity, 538 feet per second, minus 231 feet per second. Alright, we got tornado drill. Since we haven't been blown away by a tornado here, we'll carry on. So we're dividing our tangential velocity difference here by the specific heat times our total temperature. And we had previously looked up the specific heat based on our inlet temperature to be 0.2483 BTUs per pound mass degrees Rankine. And our total temperature we just calculated to be 945 degrees Rankine. Once again, we have to be careful with our units. So we're going to have 778.2 feet slugs feet per second squared. We're kind of taking our conversion here and blowing it up. Divided by 1 BTU. That's our first conversion. So it's really 778 foot-pounds force per BTU, but we've already spread it out. And then times 32.17 pounds mass per slug. So just checking things out in the denominator here. Of course, the BTUs will cancel, pounds mass will cancel, degrees Rankine will cancel, slug will cancel, and we're going to be left with feet squared per second squared, which is the same as what we have in the numerator here. So we're in good shape. And of course, that whole thing, we are adding 1, and then raising it to the gamma over gamma minus 1. So 1.381 over 0.381. And evaluating that, we'll get PT2 over PT1 is equal to 1.152. And so that gets us our total pressure ratio across the stage. If we also want to know the actual exit total pressure, we can put in that PT2 is going to be equal to, of course, that ratio times PT1, so 1.152 times 167.1 psia. So we get that our discharge total pressure here is going to be 192.5 psia.